The reason I wanted to mention that is that I thought I'd at least say something about power transfer from a power plant that PG&E owns over to Davis. And so what do I want to say about it? Well, just really schematically, you know that a power plant, I shouldn't put a battery there. I should put an AC source because that's what it is. So let's call this an AC source and forget that I drew a battery. I did that this morning, so I wasn't thinking. These wires are miles and miles long. Davis is nowhere near the power plant. So the wires to Davis are miles and miles long. At some point, you cannot neglect the resistance of the wire. Wires have resistance, and if they're miles and miles long, it's going to start to have an effect, and they're going to heat up a little bit, and PG&E is going to dissipate power into the atmosphere that they'd like to sell to you. So they're going to lose that. They'll lose the ability to sell that because you don't care if the air gets just a tiny bit warmer somewhere in I don't know, Ceres, somewhere out of town, somewhere else. So what I've done is I pretended that these wires had zero resistance, and then I put a resistor in just to compensate for that because there is a resistance in this circuit. It's the wires. So I just put it in there and say, this is the total resistance of the wires. We'll just pretend it sits right there. Nothing else in this thing has resistance except for Davis, the city. Every time you plug stuff in, it uses energy. And so I'm using this resistor as a way to model what the city of Davis does in terms of taking energy out. It doesn't just take energy out in terms of resistors. It does a lot of other things with the energy, but let's just pretend it's a resistance. So the difference here is that there's a AC voltage supplied in this circuit by the power plant. Again, this is a little bit simplified. I'll tell you how in a second. And then there's another circuit that's connected to this main circuit by a transformer. These two coils, I didn't draw the chunk of iron that goes in between them, but those two coils next to each other represent a transformer, something that changes the voltage. So this is a question about the power lost that PG&E can't charge for. Power dissipated in the wires. It's lost to thermal energy in the wires. It's lost in that resistance. You know that the power lost in R depends on I squared, the current through those wires. So is it better to transmit power at large voltages or at small voltages? So that's what I'd like you to answer. I have a feeling that you know the answer already if you trust PG&E to have made the right decision, and they're still in business, so they probably did. But still, I'd like you to think of the physics of why this is true rather than what the answer is that you may already know. Should power be transmitted at high voltages or at low voltages? From PG&E in those long lines that go through the countryside. So the main answer is large voltages, although there's a significant group that says small voltages. Let me step back here. Suppose you have, so I mentioned these that this is a better way to talk about it. Suppose you have the primary, well, let's just do this. Here's a primary that has a small voltage, and the secondary has a big voltage. The primary has a big current because the power, There it is. The power is I times delta V. Power is I times delta V. So the primary with the small delta V has a big current. The secondary with the big delta V has a small current. And basically, that's what's going on here. The Davis is on the small voltage side, big current side, and this thing is on the big voltage. This thing is on the big voltage side and small current side. So a big voltage and a small current at this transformer goes to Davis, which is a small voltage and a big current. So you want the small current side for low power losses. You're putting a small current, oscillating a small current through those wires at a very high voltage. In fact, those wires that go through the countryside are at hundreds of thousands of volts. So the reason they're at hundreds of thousands of volts is so the current through them will be really small, and they won't lose very much energy because of the resistance of the wires. The rest of this is the effects of having to use voltages of hundreds of thousands of volts. You can't have hundreds of thousands of volts coming down into these two things here. That doesn't work. You don't even want hundreds of thousands of volts in the city of Davis. So somewhere on the edge of the city of Davis is, I've left stuff out here, somewhere on the edge of the city of Davis is a transformer, or a whole bunch of transformers that take hundreds of thousands of volts and turn them into 1,000 volts or something. Then a bunch of the lines through Davis, the main lines, are up at something like 1,000 volts coming through Davis. Again, as high as you can stand to keep the currents down, to keep the losses down. And then outside your home or every block or something, I don't actually know how big these are, but periodically in town are transformers that take it from 1,000 volts down to 100, basically, 200, something like that. So there's not really one set of transformers. There's at least two sets of transformers that take these giant high voltages down to voltages that go into your outlets.